Now that we've talked about cross products and dot products, now I want to introduce how we represent planes in space. But before we do that, I want to go over the combination, a concept that combines both the dot and cross product. And this is called the triple product. So first, let's remember that the cross product of vectors A and B, given their components, and these are three-dimensional vectors, their cross product, which is a vector, is given by this, which we know can be found by a determinant. This is the component form of the cross product. Now, say we take a third vector, call it C, and we take C dotted with the vector A cross B. Remember, the dot product takes in two vectors, and it will return a number. But remember, the dot product, when you take the components of the two vectors that you put in a dot product, you do component by component multiplication, meaning that given the components of C being C1, C2, and C3, you're simply going to multiply the respective components of the second vector, which in this case is A cross B. And these squiggly lines are just me not wanting to write all this again, but so just remember this is when you take a cross product and you dot it with a third vector. This is what it would look like. Now, let's take the determinant of the same vectors that we use for this triple product, remember? So the first row, I'm going to call this represents the C vector. Second row, the A vector. Third row, the B vector. But what happens when we do take this determinant is, if you remember how to do it, it'd be take this, go by the first row, take the first element, delete the row and column that element is in, and then you take this remaining determinant. That would give you pretty much what's in this first element. And now for the second element in the first row, delete the row and column that element is in, and then you take the remaining determinant. And then same thing for the last element of the first row. You delete that row and column, take that determinant. Each of the determinants is 2 by 2. And eventually, you would find that the determinant given all three of these vectors will return the same thing as the triple product. Mathematically, what this means is that the scalar given by a vector dotted with a cross product will be the same thing as the scalar given by the determinant of all three vectors. It's important to note that the determinant itself doesn't return a vector. Last video in the cross product, the determinant, it was used to find a vector, but what we did with the determinant in cross product is that the first vector in the first row, it was the unit vectors I, j, and k. And eventually it returned a value that was something multiplied by I minus something multiplied by j plus something multiplied by k. This itself, it is a scalar because we're adding multiple things together. This itself isn't a vector, but when we see this, we know that it represents a vector. But in actuality, the determinant returns a scalar value. Given the triple product, now we're going to look into a very special application of that concept there. So let's say we're given three vectors, and we know that two vectors, they span a parallelogram. Now, three vectors, they span a parallelopiped, which is what this object is right here. It's called that because each of the faces is a parallelogram. Now, we know how to calculate the area of a parallelogram spanned by two vectors, which is the cross product, or its magnitude specifically. Now, we want to find the volume of this object. So the general formula for the volume of a parallelepiped is the base, the area of a base. It can be any arbitrary base, multiplied by the height between the base and the opposite side. So what we're going to do is abstract that to the vector world. We know how to calculate the area of this parallelogram spanned by A and B. That's just the magnitude of the cross product. Now, all we need is the height from the parallelogram to the opposite face. Notice here, I've also drawn the vector that represents the cross product between A and B. what I'm going to do is I'm going to take just the cross product and the next vector, vector C, which in this case it's not coplanar with A and B, meaning that there's actually a height to this vector in relation to A and B. So what I'm going to do, I have this right triangle here, and we're given, if we know the angle between theta, between vector C and the cross product, let's say this segment along the cross product between A and B, right here, that point that ends directly at the height that C vector ends, that's the height that we're looking for. If that doesn't make sense, just remember there's just an altitude, but in the 3D sense. So we know that A cross B is going to be perpendicular to A and B. Therefore, the height is going to be along, or at least parallel to A cross B. That's why it's along A cross B. So again, we know what we're looking for, which is the height, and we have theta and C vector. So what I'm going to do is I just take the cosine of the angle theta, which is going to be h divided by the magnitude of C. And rearranging that equation, we get h is equal to the magnitude of C times the cosine of theta. Now we have what we're looking for. So again, the volume of this object is going to be the area of the base times the height. The magnitude of the cross product between A and B is going to represent this area, just the magnitude. And then we have the height, so we're just going to put that together. So the magnitude of A cross B times the magnitude of C times the cosine of theta. C cosine theta, again, that's the height. That's going to represent the volume of this box, or parallelepiped. The thing is, this formula here, it's very familiar. Remember, the dot product the geometric representation of the dot product is the magnitude of the two vectors you give it multiplied by the cosine of the angle between them. And even though this is just the cross product of the two vectors, it's still one quantity itself, and it's a magnitude. So if we're saying the magnitude of this vector times the magnitude of this vector times the cosine of the angle between them, that's a dot product. And so that'd be the dot product between C vector and the vector A cross B. Therefore, the volume of this parallelepiped will be given by the triple product, or the dot product of the cross product of the three vectors. And it doesn't actually have to be in this order either. Say if you wanted to take the cross product of B and C first, and then your third vector will be A. It'd be A dotted with the cross product between B and C. You can do any combination of the three. It'd be like, what, 3, choose 2, which is just 3 different ways of rearranging the triple product. If you wanted to include negatives, it'd be like 6. So you can have 6 representations of positive and negative volumes. The last connection I want to make is, again, we know that the triple product can also be represented by a determinant of the three vectors. Therefore, all 3 of these quantities, they will give you the volume of this parallelepiped. So you can take the determinant to find the volume, or take the triple product. But yeah, that's kind of the culmination of using the dot and cross product. And if you don't take away anything from those 3 concepts, take away how to find the volume of this little party trick. Now we're going to talk about planes. So the first thing I want to do before I introduce how to represent planes in 3D space is the idea of unique geometry. For a geometry to be unique, that means there's not going to be anything else like it. There's only one thing that all representations will lead to. So for example, if you've taken a basic geometry course, you know that for a line to be that one line, there has to be 2 points to define it. If you take 2 points, draw a line between them, that's a line. You can't move that line, rotate it in any type of way without changing where those 2 points are. Now, if you want to talk about a plane, you can't just have 2 points. If you have 2 points, say this marker is a line in space determined by its 2 endpoints. The thing is, there are an infinite amount of planes that go through this one line just by rotating it. So we're going to need another condition to have only one plane have only one plane that's unique. And what that's going to be is a third point. So 3 points determine one plane. Just try to imagine taking any 3 points in space, and you can't have more than one plane between all 3 points. That's actually the idea behind tripods. Tripods are ideal for balancing something in that like context, like a camera, because if you had four points, it'd be a little bit off balance, and there's a chance that the fourth point won't be on the same surface, considering you're on a flat surface. But if you only had 2 legs, then that that bipod is gonna fall over. So three legs or 3 points is ideal because there's only one flat plane determined by those 3 points. Now we hopefully have that understanding. We're gonna move on to a plane in 3D space. So say we're given P1, P2, and P3. We know these are 3 points that have to lie on the same plane, and that this plane is defined by these 3 points. And there's only one plane like this. So what I'm going to do is I'm going to introduce a 4th point. Remember that this 4th point may or may not lie on the same plane as these 3. 4 points aren't guaranteed to be lying on the same plane. So what I want to ask is, does this point P with X, Y, and Z coordinates lie on the plane defined by P1, P2, and P3? So I'm going to take this idea that I just introduced, the triple product. If you can imagine the vectors from P1 and P3, if we have the third vector from P1 to our 4th point P, if P is on the plane, then that basically means the 3D object, the parallelepiped, squished down into one flat plane. And what a flat plane means in this context is that the volume is 0. The same way if you had a 2D object and you smushed it into one dimension, it'd have an area of 0. So again, we're just saying that the vector from from the tail point to our 4th point, when you take the triple product or the volume spanned by all 3 vectors, that volume is 0. So what does this mean mathematically? Remember, the volume is just can be written as the determinant between the 3 vectors that we use for the triple product, meaning that the determinant of the vectors P1 to P2, P1 to P3, which are both in the plane, and then our third vector P1 to P, our 4th point, which may or may not be coplanar with the first 2 vectors, that determinant is going to be equal to 0. What we could do is rewrite out this whole thing and do the cross product between all 3, or do the determinant between all 3 vectors. That would eventually give us something that would give an equation that determines a plane in 3D, which we'll get to. But not only do I not want to write all that out, but there's also a different way to get to the same answer. I'm going to introduce the idea of a normal vector. So again, we want a unique plane, and imagine a vector that points perpendicular to that plane. We can move this vector along any point on the plane. However, if you notice, this marker is in the same direction no matter where I put it on the plane. That means that the vector that's perpendicular to a plane can also uniquely describe the plane itself, because the normal vector doesn't change. Vectors, they only care about the direction, not the position at which they are in space. So again, the normal vector, the vector that points perpendicular to a plane, is also a unique representation of a plane. So given that, go back to this image right here. This blue vector will be the vector perpendicular to the plane, vector n. That means if we have the normal vector and then any vector that's coplanar, or that is determined by points on the plane, 2 points, any vector on the plane is going to be perpendicular to this normal vector, if you can imagine it. So, for instance, P1 and P3, we know these are points that are on the plane, and that vector is going to be is perpendicular to the normal vector. Same thing for P1 and P2. Again, the question we're asking is P on the plane? If that means if P is on the plane, that means the vector between a point that's already on the plane and P has to be perpendicular to the normal vector. Again, we want to explain this concept mathematically. So that means if P1 to P, that vector is perpendicular to the normal vector, that means their dot product is equal to 0. I'm going to expand this equation right here. It's going to be a lot easier than what I was going to do here, but it is actually going to give the same equation that represents this plane, defined by P1, P2, and P3. Before I expand this equation, I want to explain furthermore as to how these two equations are going to lead to the same place. And what I'm going to do is I'm going to connect them by an idea we already know, which is that the cross product between two vectors is a vector that's perpendicular to both of them. So if we know two vectors that are coplanar, we know that the normal vector of the plane is going to be the same as the cross product between the two coplanar vectors. What that means is vector n is equal to the cross product of P1, P2 cross P1, P3. So if we take this idea of the normal vector being perpendicular to any vector in the plane, then it's saying this vector with our fourth point dotted with n is the same thing as the vector dotted with the cross product. Now remember, this is our triple product, or our volume, whichever way you want to interpret it, which is ultimately the determinant of all three vectors that we used in the triple product. So that's the connection between this equation and this equation. They're ultimately saying the same thing, which is why they're going to lead to the same equation of a plane. What we're looking for is a mathematical description of what we just said. So we're going to start with assigning values to our points and our vectors. So we're going to let P equal an arbitrary point in space with coordinates x, y, and z. And then P1 is going to be our point that we know is in the plane. Call that x1, y1, and z1. And finally, we're going to let our normal vector, which is, remember, this is a vector, not a point. It's going to have components a, b, and c. Now that we have that, we're going to need to represent the vector between P1 and our arbitrary point P. And pretty much if you have two positions in space and you want to find the vector, what you do is you simply just subtract each respective position, which what that means is just we take the position of P and from it we subtract the position of P. Sorry, we start with P1 and subtract from it the position of P. What that's going to give us is the vector from P1 to P is equal to x1 minus x, y1 minus x, and z1 minus x. So now we're going to take our dot product equation here, and now that we have actual values, we can expand the dot product into the component form. Because our components for n are a, b, and c, we can just multiply the respective components of each vector. All this is the component form of a dot product between this vector and the normal vector. And now we've arrived at an equation. Remember, we started with a vector that we don't know is on the plane, dotted with the normal vector of the plane, is equal to 0, which means that our arbitrary point is on the plane. This statement being true means that our point is on the plane. And what we've said now is that given that our point is on the plane, any point that we select with arbitrary values x, y, and z have to satisfy this equation. And what we've done now is we've arrived at the equation of a plane. So again, what are we actually looking at here? This is an equation of a plane, but what do we actually do with it? So imagine if you're given points x, the points in red, x, y, and z, which are going to be variable. Every triple of x, y, and z that satisfies this equation, and all this is equal to 0, that means that triple is on the plane here. So this is all values of x, y, and z that satisfy this equation are all values that lie on this plane, which is why it's the equation of a plane. It's not really a function. It actually can be expressed as a function because we have a linear variable for z, but this is a standard form of a plane. Later we can talk about how we can graph planes as functions, but this here is just all values of x, y, and z that satisfy this equation. Hopefully that makes sense. If you wanted to start with this equation from the determinant, it would eventually lead you to the same exact place because you'd have values for P1, P2, and P3, and then same values for P that we used here. And eventually, if you just expanded that determinant, it will give you this equation right here. If you want to do that on your own, go ahead. I will not be though. In summary, what we've talked about is how we can incorporate the dot product and the cross product into one triple product, which can then be expressed by a determinant of 3 vectors, which can then express the volume of the object spanned by all 3 vectors. And with that volume, we talked about how we can determine if points are coplanar with each other or if a point lies in a certain plane that's already defined. And from that, we derived the equation of a plane. So when we're given a normal vector to a plane, or a plane that's already defined, and then a point that's on the plane, or actually just the normal vector of a plane, we can determine an equation that describes the set of all points that are in the plane.